Okay, welcome back for the next tutorial. Last time we left off, we were talking about 7-segment LEDs. We had one hooked up with 7 digital pins, and doing the math real quick, 7 digital pins would be 70 pins per bedding station, and that's way too many. Arduino Mega has 53 digital pins, and obviously 70 is way too many. So we need a way of decreasing that number. The way we do that is through this little guy right here. It's called the shift register. And the shift register is going to take it from 7 pins down to 3 pins. You can find shift registers on eBay. Here they are, 50 of them for $3.80. Whatever that is, less than 8 cents each. So, pretty good deal there. I'm pretty sure I bought them at Radio Shack before. I think they were a couple dollars there. Or I'm sure your local electronics store has them if you just want to try one. So let's go ahead and hook this thing up. Let's see, power to my board is off, so I'm going to go ahead and hook this up. First thing I'm going to do is ground. Ground needs to go to pin number 13. So the way the pins work, there's a little notch at the top, and there's also a little indentation, and that means this is pin 1 over here. So it goes 1, 2, 3, 4, 5, 6, 7, 8. Skips over to this side, 9, 10, 11, 12, 13. So 16, 15, 14, 13. I also need ground on pin number 8. And I also need ground on my 7-segment LED, which we established last time was the third one down. Might be different on yours, but on this one it's the third one down. I've got a few of them with different pin patterns, so pay attention to that. I need 5 volts going to pin number 16. And I need 5 volts going to pin number 10. Right there. Okay, so we said we're going to take it from 7 digital pins down to 3. So let's hook up the 3. 13 is going to be the data pin. That goes to pin 14 on the board. 14 on the chip. Pin 12, the latch pin, goes to pin 12 on the circuit here. And pin 11, which is the clock pin, goes to pin 11 on the chip. Okay, besides hooking these pins up to the 7-segment LED, it is hooked up, so we can start writing some code. Okay, so last time we didn't really talk about it, but we used something that was called a variable. We used count was equal to 0. Variables are basically words with varying amount of values. Integer variable, or an int, is a whole number, no decimal points. There's also Boolean, which would be true or false. There's string, there's float, which would be numbers with decimal points. There's byte, and there's more that I'm either not thinking of or don't know or forgot. So integer and Boolean are the only two that I'll use throughout any of these programs. Also last time, or last couple, we used anytime we wanted to write something to a pin, we just used the pin number itself. So digital write 13. It's fine, you can do that, but the better way to do it is if you declare the pin as a variable. So data pin, we're going to make 13. That way, if you have to make changes later on, if you need to move you know, your wire from pin 13 to pin 5, you don't have to go through all your code and change every 13 to 5. You can just change it right at the top here. So we got the data pin is 13, the latch pin is 12, and the clock pin is 11. And just as we did before, you have to declare the pin mode. Pin mode of the data pin is output. All three of these are going to be output. Latch pin is output, and clock pin is output. There we go. All right, so let's on the shift register, the latch pin is kind of the gatekeeper. If it's set to high, it's not going to allow any data to pass through it or to change any of its values. But if it's set to low, it will allow you to change its values. And we need a new variable here, and it's going to be a byte. We need a name for the byte. Oops. That is going to be, I'm just going to call it number. It's an array, so it needs those over no volts. So for right now, I'm going to set all 8 pins as high. I believe that's 8. 1, 2, 3, 4, 5, 6, 7, 8. So now we got a new number here. So let's shift out is what we need, the command we need. We're going to tell the data pin and the clock pin, and then there's this thing MSB first. I have no idea what that means. I never looked it up. I just know that it needs to be there. I'm sure if you ask someone, they'll know exactly what it means. But yeah, I never really cared. I just know that it needs to be there and it works. All right, so let's look at this number and then 0. So 0 means the first value in the array. In binary, everything starts with a 0. 0, 1, 2, 3, 4, 5, 6, 7, 8 is how it counts. So 1 is actually the second value. So the first value here is 0. When we add a second value here, that would be 1. A third value, that's 2. But we only need one value for right now, so that's value 0. Then we need to tell the latch pin to go back to high and not allow any more values to go through. And then we'll just delay for 5 seconds so it doesn't continuously write that to the shift register. Okay, so let's plug in the board and send it to it. Alright, so nothing should happen right now except for all of my pins are set to high. So let's take a look here. So the first value, or I guess it would be the last value, the one on the farthest right there, that corresponds to this pin right here. This is pin number 15. Just to make it easier, I don't really use that one. We're going to leave it blank. We're going to start with pin 7 here. I'm just going to poke around until I find one that lights up. There we go. That one lights up right there. In a real circuit, there should be a resistor separating this wire and the LED to protect it. But just using this as an example, so I'm not really doing any resistors. Okay, second one here, pin 6. That's the decimal point. I don't really have any need for the decimal point, so I'm not going to hook that one up. Alright. I don't know why you would need a decimal point on this one, but if you did, you could hook it up to pin 15. Third one here, where am I on? Pin 5. No, no, yes. Pin 4. I think I'm at the highest one over here. Yep. Let's go over to this side. There we go. 3. No, 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 yes. Pin 2. Yes. And I missed the middle one somewhere. Where's the middle one? Let's see. Here? There you are, right there. Okay. So the way they're hooked up to this LED, I mean, as long as all 8 are connected somehow and throughout all of your boards or your circuits, they're the same. It's not going to really matter. I'll show you how to figure out which pin corresponds to which LED right now. Okay, so we have them all set at high. Let's change only one to high. So we're going to go 0, 2, 3, 4, 5, 6, 7, 1. Upload that. And that corresponds to pin 15, so nothing should be on. Let's go ahead and check to make sure that worked. And go ahead and plug one into 15 here. And then the decimal point, I believe, is that one. Yeah. So pin 15 is on, but we don't really use that one, so nothing there. So let's change this to 1 0 as opposed to 0 1. So 10. 6 zeros and then 10. And see which one lights up. The middle one. So G is 10. Let's change this to 5 zeros and then 100. A 100. 4 zeros, 1000. B, nope, it's F. I'm sorry, yeah, F is 1000. I'm working upside down here, so I'll mix it up. 3 zeros, 10,000. Is E. Two zeros, 100,000. 4, that's correct. All right. B is 100,000. One zero, then 1 million. C, 1 million. And $10 million, with any luck, should be D. And it is. Okay, so what do we need to change this number to get a 0? Do we need the 10 million number? Yes. Do we need the 1 million number? Yes. Do we need 100,000? Yes. Do we need 10,000? Yes. Do we need 1,000? Yes. Do we need 100? Yes. Do we need 10? No. And then the final one, which is the decimal point, or we don't really have it hooked up, is a 0. So if we upload this, we should see a 0. And we do. Let's do a 1. 0B. Do we need 10 million? No. Do we need 1 million? Yes. 100,000? Yes. 10,000? No. 1,000? No. 100? No. 10? No. 0? No. Let's go ahead and do 2. 0B. See what a 2 looks like. Alright, so a 2. Do we need 10 million? Yes. Do we need 1 million? No. Do we need 100,000? Yes. Do we need 10,000? Yes. Do we need 1,000? No. Do we need 100? Yes. Do we need 10? Yes. We don't need the decimal point. 3. Do we need 10 million? Yes. Do we need 1 million? Yes. Do we need 100,000? Yes. Do we need 10,000? No. Do we need 1,000? No. 100? Yes. 10? Yes. 0? No. 4. Zero B. All right. Do we need 10 million? No. Do we need 1 million? Yes. Do we need 100,000? Yes. Do we need 10,000? No. Do we need 1,000? Yes. Do we need 100? No. Do we need 10? Yes, we do. And 5. 0B. 10 million. Yes. 1 million. Yes. 100,000. No. 10,000. No. 1,000. Yes. 100. Yes. 10. Yes. Last one, 0. Alright, so let's bring our old friend count back. I'm going to set it to 0. And we're going to change this number here. We're going to change that to our variable count. We're going to change it just to a second delay as opposed to a 5-second delay. We'll add 1 to count every time it comes through. And if count were greater than 5, since we don't have any variables set up, greater than 5, we'll set it back to 0. With any luck, we should count 0 to 5. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. Perfect. And hopefully from there you can figure out how to make it to 9. So obviously we can't put this breadboard behind our wood and inside the derby. So we have to look at making something like this guy right here. This is called the PCB. Make your own printed circuit board. These are sockets for the chips here. You don't have to use them. You can solder them directly into the board if you want, but I figured one would ever fail, I could just pop it out and put a new one in and it should work fine after that. In my later models, I ended up putting this socket on the other side here, so that way the 7-segment LED can be higher for the piece of wood that it goes through. So those are the solders on the other side, and then wires, you need this one and then one ground, and then your 3 data cables to go to the Arduino. That's pretty much what it's going to look like right there. those boards, if we go to eBay here, 50 pieces, $8.77 from China. That makes it less than 16 cents a piece. And with those, with your shift registers, with your 7-segment LEDs, you need some wire, some solder. Hopefully you have a soldering gun. If not, they're pretty cheap. Harbor Freight probably has them for $10. You can make all 40 of these boards for probably $25. It is a lot of work. It is not much fun. It's very mind-numbing. You can do it if you want to save money. If you don't really care about money, you can go to lucidtronics.com. This guy already has the boards made. The circuit board's made. You still have to solder in the resistors. There's a capacitor in there, but it comes with the 7-segment LED, with the shift register, with the boards, and you just solder everything in there. It only takes a couple minutes to solder. They're pretty easy. Has the same 3 hookups, and the power and the ground. They work great. They're really easy. If you look over on the right here, $7.95 each. For 40 of them, what's that mean? $318. So $25 or $318. What's kind of comes down to you? What's your time worth, and what's your frustration and aggravation level? If you look up in the top left here, you'll see just a small picture of 2 daisy chained together. So if you did want to go higher than 9 bets, these would be nice, because you don't really need anything additional. It looks like you still use the 3 wires, and you can still get it 9 or more bets. A lot more expensive option, but definitely one to consider. And if you make a few boards and you hate making them, then you can look at something like this. That's it for right now. Next, we're going to hook up a switch. So, see you then.